Okay, we've got a 30 kilowatt, 240 volt long shunt compound generator. We have a lot of losses to calculate. We've got our armature resistance at 0.075 ohm. Series field resistance right up here, 0.065 ohms. You've got your shunt field at 150 ohms. Our rated mode, 30 kilowatts and 240 volts. I put all the givens up here in green. All right. A lot of things we know from this, from series and parallel circuits, right? Applying our series circuit rules and applying our parallel circuit rules. What do we know about the voltage on the shunt field and the load?
It's the same, it's in parallel.
It's the same, they're in parallel, okay? So we can write that up here, 240 volts, right?
Yes.
How about IT? What does IT equal to?
IF plus IL.
Okay, IT, I'll write this over here, IT equals IF plus IL, okay? Do you need much of anything else to start solving these?
No.
No, okay? Now I'm going to move over here and we've got our line ladder and the matrix there. Okay? Put these items up here. Parallel circuit rules, these two are the same, so I could write 240 volts up there. Correct?
Yeah.
Okay? Now I've got two items here for the load. I've got two items there for the shunt field. I can use Ohm's law to fill in the missing blanks, right? Okay? Now, what do we have for current there?
125.
Okay, I is equal to P over E, right? Works out to be 125 amps. I is equal to P over E. 30,000. Right, 240 volts. 125 amps. Done. Okay? How about over here? Well, now you got I is equal to E over R. 240 divided by 150. 1.6 amps. Right? Okay? 1.6 amps. Now we already put this formula over here. IT is equal to IF plus IL. Okay? Is IT the same as your RA and your RS? It's the same as your currents in each of those.
Yes.
Yeah, it's a series circuit at that point, right? Okay? So, what do we have? We've got 126.6 amps, 126.6 amps. Okay? Now, what do I have here? I've got two items for this series resistance, and I've got two items for the armature internal resistance. Go through and do our math. E is equal to I times R for this one, and E is equal to I times R for that one. We come up with 8.229 volts and 9.495 volts there. How about power? We need to calculate power because we're going to be looking for all of our losses, right? Well, down here, what's your power? I squared R? I squared times R? Can you guys do that? Power, easy, right? Okay, we should have 384 watts there. 1042 watts on that one. 1202. 1,202 watts. Okay? Now, can we look at this and our total power out here is the sum of all of these powers here, right? I don't have enough room on that, so I'm going to break that and put 32.63 kW. Okay? Our total current is the same as this current here, 126.6 amps. You add up all the watts. Just add up all the watts. Just add them all up. Okay? Now, our total voltage, we've got 240 plus this voltage drop plus that voltage drop will be equal to our generated voltage inside the armature. Okay? 240. We don't add the 240 twice, do we? Because they're in parallel, it's the same voltage. So 240 plus 8.229 plus 9.495 gets us a nice 257.7 volts. Okay? 257.7. That's what we generate. That's what we have to generate to overcome the voltage drop in the armature, overcome the voltage drop in the series field, and provide 240 volts to the load. Okay? Hey, that's one of our questions over here. E.g. 257.7 volts. There we go. I'm not going to move the camera on that just yet. Okay? Now, how about the brush voltage across the brushes? All right? The voltage across the brushes are right here at A1 and A2. So if I put a meter here, that's what we're looking for as far as the voltage across the brushes. Okay? You can approach this in two ways. Two ways. You can come from the outside in, or you can look at the generated voltage minus the voltage drop. Okay? The generated voltage minus the voltage drop in the armature is what will be presented to you at the brushes. Okay? So the generated voltage minus the voltage drop inside the armature. Okay? So what are we looking there for the brushes?
248.2. 248.2.
248.2. Okay. So did you do that by EG minus RA?
Yeah. I did the shunt plus the.
Oh, you did it the other way around?
Yeah.
Okay, you went 240 plus this. Okay.
Same thing, though.
What do you get when you do 257.7 minus 9 point?
Same thing.
Same thing, right? Okay. All right. Total copper losses. Okay. What's a copper loss?
Loss in your fields.
The loss in the wire. It's the loss in the wire. Each one of these have resistances, right? Each one of them have current going through there, right? Copper losses. I squared R. Okay? That's your power loss. I squared R, I squared R, I squared R. Okay? You've got your shunt field that you need the loss on, the series field that you need the loss on, and internal on the armature. Okay? These three right here. These three right here are your copper losses. If I add up those three, if I add up the power loss in the armature, plus the power loss in the series field, plus the power loss in the shunt field, that will be my copper losses.
How come you don't have the last digit?
I don't add the last one here because that's going to the load. That's my useful work. That's the good stuff. Okay? But I have to generate this in order to get this. Okay? So, copper losses. Will be 2628 watts. 2628 watts, right? Okay. So, almost there, aren't we? Okay. Now we've got the horsepower of the prime mover. Horsepower at the prime mover. We show the efficiency of this is 79%. Okay? Looking for a place to write. I'm going to erase all of this. Everybody has those. Okay? Horsepower. What are we getting out of here? Power out. $30 kW. Power in. We don't know, right? Efficiency? 79%. That's what we're given for this part of the problem. Okay? So we set this up and say our power in, power out, divided by your efficiency. 30,000 divided by 0.79. What's our power in? What do you get there? 37,975? 37,975 watts. Is that horsepower? No, it's watts, right? Watts. How do I convert watts to horsepower? We have 746 watts per horsepower. So if we divide watts by watts per horsepower, we will get horsepower. Okay? We come up with, I'm running out of room again. Okay? Okay. The horsepower is going to be 37975 watts divided by 746 watts per horsepower. The watts cancel 1 over horsepower. We come out with horsepower, right? Horsepower 50.9 horsepower. Okay. That's the entire problem.
So you could just calculate the horsepower before we even do the rest of the problem, because I mean,
In this case here, yeah.
30K is just getting
If you're totally stuck, at least you can get the horsepower.
some points out.
Yeah.
So why are we only using the load wattage and not the whole wattage? Because technically isn't giving out like 32,000 watts?
Yeah.
It's generating 32,000 watts. You're seeing we have to put in 37,975. So if you look at the total loss chain of this, we're going by power out. Okay? This is our useful load here. That's part of our loss, that's part of our loss, that's part of our losses. Then you have the friction losses, you have the windage losses, you've got the brush losses.
So efficiency only talks about what's at the load.
Efficiency is your final output at the load, okay? Versus the power you have to put in, okay? If we take all of this, okay? If we take all of this, we know what our copper losses are, right? What did we say our copper losses were? 2628. We know our power in is 37,975. Okay? In this case, 37,975 minus the 2628 will give you your non-copper losses. Eddy current losses, windage losses, friction losses, all those others. Okay? And in this case, that's pretty darn bad.
5,000.
About 5,000 watts of heat generation. Yeah, the efficiency, I purposefully lowered the efficiency on this one. Okay?
Oh, Scott, so A, the armature current is 126.6.
The armature current is 126.6 amps. Okay? Other questions?
Can you explain what you said about if you take the watts and subtract by?
Okay? If you have 37,975, that's the power in. Right?
Okay.
Minus your 2628. That's the power in the copper.
Right.
Okay? What are we left up with there?
Would it be power out?
Okay? We're left with, oh, let me start all over again. Okay? No? All right, it's fine. We're there. What number do we come up with here?
35,347.
35,347. Minus 30,000. That's your power out. Right?
5,347.
5,347. That's other losses. Okay.
Other losses we haven't found out yet.
The other losses are your mechanical losses, your eddy current losses, different, your windage loss, your bearing
It's like
losses.
that's what they mean by strays? Like your
Exact-
stray losses?
Your stray losses are another, yeah, another source of loss.
I got a question on the chapter. It said, this is rate the efficiency at, what's the efficiency at a